Hello, everyone. Welcome to the Rock and Roll with NASA Challenge webinar. Thank you for taking the time to join us today. Please feel free to say hello in the chat. Let us know where you're joining us from. Our agenda for today, we're going to provide an introduction of our panelists, then an overview of the challenge, along with showing you how to enter and submit your solution, and then we'll move into the Q&A portion. Please do be sure to submit your questions via the Q&A box, which you'll see along the bottom of your screen there. We may not get to all the questions on today's webinar. For those that we don't cover, we'll look to respond to them via the challenge page, and we'll also be uploading a recording of today's webinar to the challenge page. So starting off with introductions, I'm Andrew Osansky. I'm a project manager with HeroX. We're partnered with NASA to administer this challenge. I'm now going to pass it over to Ed Herrera to start off the introductions on the NASA side.
All right. Well, good afternoon. Yeah, I think we'll just go in the list shown. I'll go ahead and go first, and then Colin, if you can go next, and then we'll just go down the line and just give a brief introduction of yourself and maybe what you do related to rover wheels and mobility in general. So, like I said, my name is Ed Herrera. I'm a robotics engineer at Johnson Space Center at NASA. Over the last 20 years or so, I've had the opportunity to work on rover mobility projects that have built development rovers that have been used for planetary surface operations, planning, and evaluation. So the rovers that we built, we've tested at our rock yard at JSC, and we've also taken them out to analog sites. So this helps support the planning folks and evaluate some of the new technologies that we're developing. I'll pass it over to Colin next.
Thanks, Ed. Yeah, I'm Colin Krieger. I'm a mechanical engineer at NASA Glenn Research Center in Cleveland, Ohio. I've spent a majority of my career also working on roving vehicles and surface mobility research, as well as tire development, and have got to work on a few different rover missions. And so I'm really excited to see what you guys come up with. I think one thing at NASA is, we always looking for new ideas, and sometimes it just needs another perspective. So I'm excited about this challenge. Thank you.
Hey everyone, I'm Heather Warvack. I work out at the NASA Glenn Research Center with Colin. My background is in geotechnical engineering. I'm a subject matter expert in lunar regolith. So I work in the SLOPE facility, which is our simulated lunar operations laboratory, where we do a lot of the entire development, design, build, and testing. I worked on a couple of different flight programs, including our sample return as well as Viper. And again, looking forward to the ideas that you guys come up with.
So there. Hello, I'm Lucian Junkin. I've been in the robotics division at NASA Johnson Space Center for over 35 years, working Robonaut, rovers, and more importantly, I'm in the high bay right now, and you can see humanoids. You can see the latest rover that we built, maybe a little microchariot in there, and then the space exploration vehicle. And there's some spacesuit testing going on in Argos right behind us. So I'm super excited about the challenge. And I'm part of the teams that have built these rovers and also keep these rovers going. So super excited to be here.
I'm Ryan Stockton. I'm a robotics specialist here at NASA Johnson Space Center, primarily doing mechanical design work for the mobility systems on some of these newer rovers that we're working on. And along with that, doing other flight robotics projects as well. And I've been at JSC for a little over 7 years.
Hi, everyone. My name is Chanel Smith. I am the Open Innovation Advisor for this project. I work in the NASA Tournament Lab based out of Johnson Space Center. And I also happen to be a mechanical engineer. So I am really excited to see all of the solutions that come through.
Excellent. Thank you, everyone, for the introductions. We're now going to have Ed provide an overview of the challenge.
All right. Well, again, thank you, everybody, for joining and considering participating in this challenge. I also want to give a big thank you to NASA for sponsoring and supporting these activities. Before we get to the Q&A, I did want to go over some of the challenge goals and give an overview just to get us all kind of grounded and on the same page. So In regards to goals, there are some overarching goals and why NASA supports these type of challenges. The first one is just discover unique approaches to addressing the agency's needs, stimulating the U.S. and global innovation and entrepreneurship, engage the public in the agency's mission, and lastly, to foster a community of solvers for supporting NASA. So these overarching goals are our specific challenge aligns really well with those. So specifically for our challenge, for Wheels specifically, we're looking to use crowdsourcing methods. So this is the unique approach. So we have teams at NASA that are developing Wheels internally. We have partners that we're working with that are developing Wheels, but we're really looking at the aspect of crowdsourcing and using that aspect of it to kind of discover these overlooked solutions for flexible Wheels. So this is a phase challenge approach, and to showcase working prototypes that demonstrate a path towards flight. So here the key is demonstrate. So the intent of this challenge is not for the wheel that comes out of the challenge to be the flight wheel that's ready to go on some mobility system. This is really to demonstrate a new technology that's creative, either in the parts that are used or in the way they're used, the materials, or the design. And then the last goal here is to create a challenge that spurs innovation through competition and rewards higher performing designs. So the goal here is really just to give performance targets and give desired attributes, and let the community take that as far as they can to come up with new ideas. So we're trying not to over constrain it too much, and we want to see what crowdsourcing, what overlooked solutions, or these gems that we've been calling them, come out of this competition. Go to the next slide. Okay, here we go. So to give a quick overview before we jump into the Q&A, as I mentioned, this is a phased challenge. So right now we're currently in phase 1. So this one is really just to reward the best concepts and analysis. So we're going to have up to 10 finalist prizes and 5 categorical prizes. And then the 10 finalists will move to phase 2. And the intent is that these 10 finalists are capable of building a prototype. However, we do want to get the best ideas out there. So even if, we encourage you to, if you don't have currently the capabilities to build a prototype, we encourage you to form a team and find a way to build it. But even if you can't and you have a good idea, we still want to reward you, and we still want to see those ideas, which is why we have those 5 categorical prizes available. So after phase 1 is complete, we'll jump to phase 2. And so the finalist prizes that were awarded in phase 1 will go towards funding the prototypes. And out of phase 2, we'll have 5 finalists. We do want to see progress, and we want these wheel prototypes to succeed. So to incentivize that, we do have up to 10 mid-phase bonus prizes. And then finally, phase 3, this is where we're given the finalists from phase 2 an opportunity to give them an invitation to come down to JSC and actually test their wheels on our microchariot rover. And out of that challenge or competition, we'll end up with 1 finalist prize that comes out of that. So for phase 1, which is where we're at now, the goal for the solvers is to create an innovative wheel or tire designed to show engineering rationale and analysis. So here it's really just we can't necessarily take claims just at face value. What we're looking for is for them to be substantiated. So give us your rationale. There may be some things you can't necessarily prove, but at least give some evidence of that show, hey, I thought about it. This gives a high probability that it's going to work. based on how it was used maybe in a different application and how you're thinking about using it here, or here's some test data that I believe will, makes this material compatible and has a chance to survive the lunar environment. So those are the kind of things we're looking for. So when we're evaluating these, the ones that back up the claims that they're making are going to get rated higher. As far as deliverables go, there will be a 3D CAD model, so we can actually see the design and make sure that it interfaces well to the microchariot rover, and then there'll be the white paper that summarizes, all the engineering rationale and the design that's being proposed. And then finally, the intent for these technical requirements and performance targets, like I mentioned before, we don't want to over constrain it. So we try to keep the requirements to a minimum and just give you the performance targets, give you some of the desired attributes, and then hopefully that allows for just a broad range of solutions. There's a lot of opportunities for these wheels. Right now, NASA is targeting the lunar South Pole, so we're going to give that some preferential treatment as far as trying to hit those performance targets for that area. But if there's certain ones that cannot be met, just explain that and tell us how, what it can mean. So we are just looking for some innovative solutions to give us options to the wheels that we're already currently developing. So with that, I will hand it back over to Andrew, so we can start the Q&A portion of the webinar.
Excellent. Thank you. I'm just going to pop on the share here and just show everyone where they can learn some more information about the challenge. So this is the challenge page on HeroX. It's at herox.com/NASA rock and roll. This is where you'll find all the information you need about the challenge. Under the summary tab, you have the overview and the guidelines. This is a very detailed overview of everything that you need to know for the challenge. Please note the timeline. You can always sort of check where we're at. Of note, the submission deadline is on November 4th. And a few other sections, the updates forum, you can go to ask some questions if you do have any questions we don't answer today or that come up while you're developing your design. We also did want to call out the resource section. There's a lot of resources here for you to look through, so you might find some answers here for any questions you may have. One quick note we did just want to make, there's currently a shutdown with the US government, so some resources may not be available just during that time. So if you do see a notification it's not available, please do check back, and it should be back up online once we're through the current shutdown. When you are ready to go ahead and create your submission, just click on Solve This Challenge. It'll take you to create an account on HeroX if you don't already have one, and then you'll be able to submit your solution. All right. So we're now going to move into the Q&A portion. I'm just going to pull up the first question for us here. All right. Do you expect the microchariot to compact the lunar regolith by repeatedly traveling the same route between stations?
Yeah, for this one, I think you should make the assumption that it is not, that it's going to be used to do exploration sorties. It may be the case depending on, if, once we prove out the design and it gets assigned to a mission and then it flies, depending on what the requirements of that, mobility system are, it may be the case that, it just tracks the same path back and forth. So it may compact the surface there, but I would recommend that the assumption is that it does not.
And I'll add a little to that. Operationally, we do plan to backtrack where we go over our same path and to go down proven paths. But from this, as Ed says, from this wheel challenge, it's important that we're able to explore in the undisturbed regolith on the moon.
Excellent, thank you. Can you provide a CAD model of previous rovers to use as a starting point?
Yeah, here I would say there's probably gonna be limitations on the CAD we can provide. Definitely, if you look at the guidelines and information in there, there is a drawing of the hub for microchariot, and that may be something that we can provide the CAD for the hub, which is definitely going to be provided for the following phases, but we can look into possibly providing it now for phase one.
Another thing is that NASA does have publicly available 3D CAD models of a bunch of different assets on science.nasa.gov/3D resources. One of the ones that is available is a concept design of the SEB rover that we have in the high bay here at Building 9. That can be used for like reference if you're trying to make renders, but that is not the same type of scale that we're talking about for the wheel that we're looking for.
Excellent, thank you. All right, next question. The challenge description specifies that the wheel must be compliant. Does this requirement mean we are limited to a wire mesh spring-like structure, or is a solid disc type wheel design similar to those used on Mars rovers also acceptable as long as it demonstrates compliance?
Yeah, I think for this question, my opinion is, and I think it gets back to when we're going over the goals, the slide with the goals, is that we're looking for ideas that are different than what we're currently that are currently being developed. So yes, I think any idea is going to be accepted, but we're specifically looking for new approaches and innovative ways, even if it's repurposing something that's used in, say, a different industry and it can be applied here. Those are the kind of things we're looking for specifically.
Yeah, I have some thoughts I can add to that as well. I wouldn't say that the tire has to be kind of that wire mesh form that's mentioned. I think there's lots of different ways that a tire can be flexible or compliant. But because the things we're looking for are tires that can go at higher speeds, absorb impacts, have comfortable rides for astronauts, I think those all lend themselves to requiring a flexible tire that conforms to the terrain, which is kind of what this is focused on, which is different than what the Mars rover wheels are. So to me, that's kind of the distinction. It doesn't have to be wire mesh, but it needs to have some sort of ability to conform to the terrain.
Thank you. All right, next question. For materials, is it necessary to propose an entirely new material, or can we use existing materials, such as those previously employed by NASA and lunar or Mars rover wheels, as long as we introduce a novel geometry or compliant mechanism?
I think the answer is no. You do not have to create your own material, come up with a new material. Previous materials that have been rated for space flight are eligible to be used. You just have to explain how you're going to use them and how they're going to conform to the terrain is what we're looking for.
Yeah, and I'll add to that. Like we're talking about building a prototype wheel, designing something that can be made out of more commonly available materials is going to make it a lot easier to actually build a prototype wheel than some exotic, cutting edge material that exists out there.
And I would add to that, especially like Ryan says, the hub of the material, the hub of the wheel, if it's made from known materials that we've used in spaceflight, that is a huge benefit to being able to bring one of these wheels to life. Now, the material that we often talk about is the material that interacts with the surface, whether it be a special material or not. That's where you could really get creative and use materials that we haven't used in the past to interact with the soil.
And I'll add to that that some of the regions that we're interested in going to, the permanently shadowed regions or the double permanently shadowed regions, can get as cold as 25 Kelvin. So that's pretty cold, and a lot of the materials we have available that would be interacting with that surface would not be able to withstand that. So, like Lucian just said, be cognizant of the materials that are specifically interacting with the terrain.
Yeah, one more thought that I had on this is as you're proposing an idea, like I said, what comes out of this this phase challenge is not going to be the flight design. So if you are going to propose some material that's hard to get, in your proposal, think about how you're going to be able to demonstrate that there's a path eventually if that material is used, but think of how you're going to prototype that in the time frame of this challenge. With materials that are available, but maybe are representative of that other material that's hard to acquire.
Thank you, everyone. All right. Next question. The guidelines emphasize a wheel with specific dimensions and compatibility with the microchariot hub. Does this rule out alternative locomotion systems such as tracks or crawler mechanisms, or is there room for innovation beyond a conventional wheel as long as it meets the size and hub interface requirements?
I can give my thoughts, and I guess Ed, I'll defer to you since you're kind of started this. I certainly, I think, would be open to seeing ideas like that. I think that's really cool as long as it interfaces and kind of meets the requirements laid out in the challenge and meets the interface requirements. I don't think it necessarily has to be just a traditional wheel. I think if you have some other sort of concept that's a hybrid of a wheel and a track, whatever it is, if it meets those needs and integrates, I think that is something that would be of interest.
Yeah, thanks, Colin. Yeah, no, I definitely concur. I think if you have a new approach that hasn't been considered before, and maybe that doesn't line up with a quote unquote a traditional wheel, then I'd say go for it and propose it. At the end of the day, it is a competition, so we'll be weighing it against the other ideas that come in and weighing it against complexity and other aspects that are laid out in the guidelines. So just kind of think as you develop it, just think of what it takes to build it, part count, et cetera, weight, just kind of weighing all the aspects of the design and maybe from the the end user, what they're looking for as far as how you would sell it to that end user compared to wheels that are currently available or being developed.
And I'll add to that with if you do, and I'll use tracks as an example. Often you have a rotary actuator that actuates the tracks, but you also have something that holds the carriage. So if in your proposal you are just requesting for the carriage to have a link to the microchariot, then just propose that and say, okay, we're using the rotation of the motor, but we also need to stabilize the carriage, and therefore we would need stabilization point on the carriage. Just one example of the many ideas that might be out there.
Excellent. Thanks, everyone. All right, next question. Are actively controlled wheels with actively adjustable geometry and other features allowed? If yes, is there a power source, like a servo motor, located on the main rover body, which can control these actively adjustable features of the wheel?
I can give my thoughts. My thoughts are if you bring your own power and control computer for it, then sure. There is not any extra actuators on the chassis to be able to control something like this. There is just the spinning shaft that our hub interfaces with to rotate the wheel. But if you've got some crazy novel idea that utilizes electric actuation to change things, to change spring rates, to change the geometry of the wheel, I think if you bring all that it takes to control that within the volume of your wheel, then I think that's fair.
I would go one step further in the volume of your wheel, plus you can use micro chariot as a payload hauler to haul a pound or some reasonable amount of weight to control your active part of your wheel.
Excellent. Thank you. This one is related. You may have just answered it, but I'm going to put it out there in case there's anything else to add. But is the wheel design needed to include an electromechanical motor for the wheel and tire assembly to propel the NASA rover?
No. So the hub that you're bolting to is being driven by motors on the microchariot. So that is actually what's providing the propulsion force for the wheel. So you do not need to actually drive the wheel yourself. As long as you're bolting into that interface that we've given you, the rover will take care of that for you.
Excellent. All right. Are there any power consumption limitations if we are thinking of using an electrically compliant system?
This is exactly why Ryan and I talked about, if you bring it, then you kind of own it, and therefore you can define it, because it's a integration activity. If we're providing you basically ones and zeros in power, so if you bring the power and the computing power, then we will use it as a payload, and then you can manipulate it from there.
Yeah, so essentially you would have to bring your own battery, your own, I'll say a battery, but energy storage system. Traditionally, we think of that as a battery for something of this type. Your own control computer, your own probably radio to communicate with it. So, you're not going to be able to tie that into the microchariot, it's a flight computer. But yeah, you have to bring in all the resources you need to actuate that and control that within your wheel. And like Lucian said, if you need to mount a battery pack to the chassis is a flat deck, approximately 2 foot by 4 foot. But you would still have to figure out how to get that power to the wheel that is rotating. So it's probably a best idea to just integrate it all into the volume of the wheel. But you're welcome to propose, if you want us to do a slip ring or something like that to get power out to your device from the chassis, a chassis mounted battery pack, that's reasonable.
Great, thanks everyone. All right, next question. Given the unique challenges of lunar terrain, such as regolith, dust, and extreme temperature cycles, how is NASA approaching the trade-offs between wheel-based mobility and legged or hybrid systems for long-term exploration? Are there specific lessons from recent rover missions that are influencing these designs?
So I can give some of my thoughts. Yeah, absolutely. NASA has definitely looked into non-wheeled or non-traditional mobility systems. I don't know if there's any resources on there, but you can look up. JPL built a vehicle called Athlete, which is, of course, is an acronym. It's a six-legged robot that also has wheels and lots of tools. Viper, which is a rover built at Johnson Space Center, has the ability to kind of crawl. It has 4 wheels, but it can use active suspension and articulation to propel itself forward. And these are things that are being explored because we have seen limitations from a mobility standpoint. Most notably, the 2 of the Mars rovers, Opportunity and Spirit, have gotten stuck in really soft soil on Mars. And so there have been studies to kind of explore other means of getting through, and that swimming, crawling motion of Viper in particular has actually shown the ability to get through some really sticky stuff. So it's obviously trade-offs, that there's mass, energy, cost, complexity, risk, all those things that come into play, but it's certainly something NASA is interested in.
Yeah, there's concepts out there for like walking or shuffling robots. There's a CubeSat developed over in Europe that has this like 4 little spider legs. But a lot of those concepts are for moving some payload a very short distance. When we start talking about longer and longer distances, the efficiency of a shuffler or a walker tends to be pretty bad, such that a wheeled vehicle makes a lot more sense. But for very short traverses, there are concepts out there, but I don't think that's exactly what we're looking for on this challenge. But like Colin said, things like athlete with like leg wheels and things like that are definitely things that NASA has looked into before.
Excellent. All right. Next question. Is it compulsory to use rigid spokes, or can we provide ideas around that?
Yeah, I definitely not. I mean, you can use whatever sort of spokes you want, as long as they interface with the vehicle. That's one way to get compliance, and there's lots of wheel concepts out there that don't rely on rigid spokes. So yeah, I think you have a pretty open design space as long as it meets the interface requirements.
Excellent. Thank you. Next question. All right. Is the mass requirement a hard limit? Is there any range or tolerance we can utilize?
Yeah, so the mass requirement in this challenge falls under our targets. So those are the targets that we're shooting for. If you can, obviously, if the lighter it is, the higher you're going to get graded. But there is no limit. Just acknowledge that it is a competition, and if your wheel is 10 times heavier than everybody else's, then it's going to get scored lower. But no, their weight or the mass is not a requirement, but there was a target provided in the challenge of approximately for that wheel size what we would expect it to weigh.
Yeah, if in your proposal you have a super legitimate reason for the wheel being heavier, then communicate that to us. Like we talked about electrically actuated wheels. Obviously, it's going to take some extra weight. But if it gives you extra capability, then let us know that. Communicate that to us, so we can know that information when it comes to judging and grading these submissions.
Excellent. Thanks, everyone. Next question. Is there a torque value for the mini chariot drive we can use as a baseline for calculations, or just always assume the wheel design is the limiting factor?
Yeah, so the output torque of the microchariot actuator is no more than 70 Newton meters per wheel. So they're not coupled or anything like that. So each wheel is entirely driven independently. So it'll output no more than 70 Newton meters of torque.
Excellent. Thank you. Next question. Can we get a 3D view or other representation of the microchariot to ensure our wheel doesn't interfere with the vehicle structure?
Yeah, I think that is something we can work toward providing. We will have to get that through our export control, making sure that we can publish that picture. But in the meantime, so while we work that, in the meantime, the drawing that is provided in the guidelines does have the keep out zones that represent where the chassis is. So as long as you're not violating those volumes, you won't interfere, and those have some cushion in them. So as long as you're staying outside of those keep out zones, you'll be fine.
Excellent. Thank you. Next question. When designing the wheel screw attachment to the rover hub, should teams be concerned about balancing manual versus automated fastening methods with the limited space available for screwing? And how will this be evaluated in phase 2 testing for lunar conditions?
I believe I kind of understand the question. So like for this wheel, for this challenge, we're not worried about crew serviceability. This is if you have to manually bolt your wheel on with a bunch of bolts and torque wrench, it's totally legitimate. It doesn't need to be automated in any way in there. That's not a part of our grading scheme. So I believe that is what the question was asking.
I would add to that, if you would like to put in your white paper, if you think you have a novel way to put a wheel on a vehicle, that would be how this would be scalable. You could certainly put that into the section, but certainly for the challenge, we're giving you a hub and you're bolting it on, and That's what our expectation is. But you are free. I mean, we're concentrating on the interaction with the soil, but you are certainly free to have a interface to the microchariot, and then a novel way to attach your wheel to your interface plate.
Excellent. Thank you. And just a reminder to everyone, please do feel free to add your questions to the Q&A box at the bottom of the page there. Next question. As international collaboration on lunar missions grows, how is NASA coordinating technology and data sharing with other space agencies? Are there recent examples that demonstrate effective joint mission planning?
Yeah, I would say the best example of this are the Artemis Accords that are joint ventures between and agreements between the United States and other countries. Along this lines, for example, for mobility, JAXA is building the pressurized rover, so we're collaborating with them on those activities. So, across the lunar architecture, there are collaborations between domestic partners and international partners as well.
Great, thank you. All right, can you talk in more detail about your vision for the prototype phase and proof of concept demonstration phase?
So during the prototype phase, the winners of phase one, I think there's opportunities for us to possibly work with those teams to make sure those designs are progressing and are successful. So there may be some opportunities for us to provide guidance there. Once we move into phase three, we can help with the coordination of getting the hardware to us, addressing any specific challenges unique to the design. Like there was the talk about having actuated features. We'll have to kind of work through some of the, if that's a design that's selected, we'll have to kind of work through some of the integration activities that happen. And once you and your team are present at JSC, that those winning teams or team, then you'll have an opportunity to mount your hardware, and then we'll provide more details in the later phases about what the what the obstacle course actually looks like. But the idea is we will be testing out at the JSC Rock Yard, which is an outdoor facility. So we'll set up a course to test different performance parameters for the wheels, and we're still working through those activities, what those look like.
A little bit of detail of if you move from the ideation phase to the prototyping phase, part of your ideation proposal is how am I gonna turn this idea that would work on the moon to a prototype, and a lot of that will be like figuring out what materials that you would use as what we call ground test units. What would we use on a ground test unit? And so you may be swapping out, you may propose titanium for the real wheel and then opt for an aluminum hub for your wheel. So you would be in prototyping mode of, okay, we're just going to use aluminum for this. And you may get, for your compliant mechanism or the things that you use for compliance, you may have a different material than what you are proposing would work in a permanently shattered crater. So that's kind of the prototyping mindset that I think that teams will be in as they turn their idea into a prototype that goes on microchariot.
Another relevant thing to kind of compare to is NASA has something called a technology readiness level, or TRL level. In the ideation phase, you're more in the 2 and 3, which is like a concept of a product, but not a lot of analysis and a lot of testing. And a lot of the vehicles we build, and just like Micro Chariot, the LTV-GT rover behind Lucian, they're in the TRL 6 level. So for this challenge, the prototype phase is kind of between 5 and 6, prototyping a subsystem or subassembly, improving it out in a relevant environment on the ground. When you start to get TRL 7, that's like demonstrating the spaceflight environment, like in a vacuum chamber, we have the real lunar simulant and things like that. We're not quite going that high with the prototype phase of this challenge. It's more about testing in a relevant ground environment. Yeah.
Excellent. Thanks, everyone. We just have a few more questions to go here. Next question, was there any unexpected wear and tear or damage to the previous lunar rover vehicle tires?
So I can start on this one. So I would advise you to look at some of the Apollo mission reports from Apollo 15, 16, and 17. The tires themselves actually did very, very well. They had chevron strips on them that were made of titanium. But if you look at some of their Earth-based testing, those strips were previously made of aluminum, and those wore right through when they were testing in some of the sandy material. On the moon, like I said, they did well, but keep in mind that that rover only went about 20 miles, and it went on the equatorial region of the moon in the Mare terrain. So that might be a little bit of a different beast than the Highland South Pole regions, the permanently shadowed regions. Another thing that did happen, the components and mechanisms, the dust is a huge issue for those. It causes a lot of abrasion, a lot of wear. Actually, one of the fenders was severely damaged. It had holes in it and wasn't operable anymore. So they actually taped a USGS manual over it to help it perform back to its original state. But yes, it causes a lot of issues with wear. The lunar soil is very granular, very hard, so you need to make sure that your materials and your mechanisms are capable of withstanding all of the abrasion.
Yeah, adding on to what Heather said, like we were talking about concepts of electrically actuated wheels, keeping dust, even for our ground testing, keeping dust out of your electronics and actuators if you do decide to build a wheel that has active components like that, or even if it's non-active, but there's bushings and bearings and pin joints and all that stuff to allow things to flex, all those things are going to get beat up by the dust. The dust we're going to be testing at the rock yard isn't nowhere near as bad as like lunar regolith simulant, but it is still not great on anything that moves, basically. If your wheel is a solid rigid structure, similar to like a Viper wheel or something like that, where there's nothing that really moves in it, it's not as bad, but that's not what we're asking for in this challenge. We're asking for a compliant wheel. So naturally that means that something in your wheel is going to have to move, and dust is going to get into wherever the relative motion is in those components.
And I'll caution, it's not just the smaller, finer particles that are an issue. If you look at some of the Mars wheels, Curiosity and Perseverance, there are rocks that are literally stuck in the wheels, tumbling around and around. So keep in mind that rocks can get stuck, and if you have a compliant tire and you have a rock stuck in there, that could change the compliance of it and also contribute to any wear issues. So keep that in mind.
Yeah, one other additional thought, and just to kind of maybe adds on to a little bit more than what the question was asking, but think about also how the tire, what the weak area is, and if it does fail, what potential hazards that could create to the larger system. So that would be something interesting if you do kind of identify a weak area. We definitely want to hear that, and how that, what potential hazards that could create, right? Depending on what type of wheel you're designing, right? If it's a pressurized system, then we want to understand, hey, if it does lose pressure, where does that pressure go, et cetera? Or I have a failure, can I keep going after that failure type of scenario? So just to add on to that question.
Excellent. Thank you, everyone. All right, last question here. Can we publish our work in a scientific paper after the competition, regardless of the results? So even if we succeed in phase 2, or if we do not, are we able to publish?
I'm gonna let Chanel take this one, but I'll start it off with yes, you on the based on what's in the challenge, you own the intellectual property. And Chanel and Andrew explain about that. But the general answer is yes, you are encouraged to share with the world what you have created.
Yeah, exactly what he said. You have ownership of your design. So beyond the competition, any use that NASA would want from the competition, they would then reach out and work with you directly beyond the scope of this competition. But it is fully yours.
Excellent. All right. Well, thanks, everyone. We are at time now. So any questions we may not have gotten to, we'll make an effort to answer on the challenge page. We do want to thank you all for your time today. Please do keep in mind submission deadline is on November 4th. And we also will be uploading a recording of the webinar to the challenge page. So thank you all again for your time.